See, for those who are online, am I audible?
Yes, sir.
Okay. See, forget about this. We saw torque is equal to Ni AB sin theta, but due to some field which I told you yesterday, what was that field? What is the field that is present inside a galvanometer? It has a special magnetic field is okay. It has a special name. It's called as, check your notes. Oh, I didn't send you the pic. எனக்கு அமிச்சு அந்த பிக்க நீ தானே எடுத்த எனக்கு அனுப்ப சொன்னல even I forgot about it. Okay, so torque is equal to theta, right? Now theta is equal to 90 degrees. What is that called as? It is because of something called as radial magnetic field. You remember this, right? Due to the radial magnetic field, when you put theta is equal to 90, it will be NIAB. And we equated this to what value? We equated this to K times alpha, where K is called as the torsional constant, alpha is the number of divisions the galvanometer has turned towards, right? So I divided by alpha is called as, there is something called as alpha by I and I by alpha. What is alpha by I? Alpha by I is, so it is called as current sensitivity, whereas I by alpha is called as figure of merit. So did you all check your notes? I mean, your lab, did you see this word figure of merit? No experiment based on galvanometer. Half deflection method again. Half deflection method. In that you will do this one. You will find figure of merit. Okay. So first what you will do, you will find the resistance of the galvanometer. From there you will have a formula based on which you will calculate I by alpha. Okay. So why I'm telling all these things is it might come in Viva. Don't look at it like a new term. So it's the same thing that is coming from your theory. Is the point clear? Now, with this, yeah. So after the galvanometer concept, what we are supposed to see is, so after the galvanometer concept, the concept we are going to discuss is conversion of a galvanometer to ammeter. Means we know that galvanometer is a measuring device. Now we need to convert that measuring device into a, galvanometer is a sensitive device. We need to convert that sensitive device into a measuring device. Means you have this, yeah, you need to convert it to this. Here the principle is going to remain the same, right? The only difference is for a galvanometer the zero is going to be at the center. For ammeter it is going to be at the left extreme, right? So when I need to convert it to this particular device, which is an ammeter, first thing is I need to know what it does not. So even before I talk about how a galvanometer can be converted to ammeter, first I need to speak about what an ammeter is. So what does this device do? So this device is going to measure current. Okay, first point is accepted. The second point is, how is this device connected across any other circuit, any other part of the circuit? So you connect it in series across the device where you are interested to calculate the current. Why are you connecting it in series? Because in series connection, current is same. So whatever the current that is flowing through the device will be the same current that will be measured by the ammeter itself. Am I clear with that? Okay, accepted. Now the next question is, since you are connecting this ammeter in series to a resistor, okay, resistor is some device I'm talking about. When you're connecting it in series, what should be the resistance of the ammeter in the first place when you consider it to be an ideal situation? So when you talk about an ideal ammeter, the resistance of an ammeter is going to be 0 in ideal condition. Why is it so? If there is resistance developed here, if there is a resistance across the ammeter, what will happen is the current that is flowing through the device might show the variation in the reading will be shown to us. So in order to that be avoided, what we try to do is we make sure that the resistance of an ammeter is 0 in ideal condition, but in reality it can't. Okay, in reality it will be slightly existing, but what we can conclude is resistance of an ammeter will be as low as possible. Is that point accepted? Right. So it can't be 0 because here we are using no ideal. Ideal is a 100% condition. There is nothing like 100%. So when it comes to the real situation, ammeter is going to have a resistance which is approximately equal to 0. Right. So having these 3 points in mind, now we need to think of converting this galvanometer to an ammeter. So I'm giving you a galvanometer. For this galvanometer, there is a resistance of Rg. Right. Now, what I need to do is I need to make this resistance of a because the galvanometer is going to act as an ammeter. I need to make the resistance of the galvanometer approximately to 0. So what should I do? Let's say the resistance of the galvanometer is somewhere around 100 to 110 ohm. I want to bring it to 0. If I have to do that, then what we can think of is take another resistor. What will you do? You'll take another resistor and connect it across this galvanometer so that the overall resistance decreases. Here comes an important question. If I give you a resistor and I ask you to prepare a combination in such a way, make the overall effect of the resistance to come down, what combination will you choose? Series, parallel, or mixed? You need to think of parallel, because what happens in a parallel connection? In a parallel connection, resistance, the effective resistance is going to be less than the resistance of each value. Is that clear? So what I need to do is I need to take another resistor and connect it in parallel to this galvanometer so that the circuit looks something like this. So this resistor which is connected in parallel is called as shunt resistor. Basically, shunt means diverting the path. So what happens in a parallel connection? The current gets diverted. So that is why this resistor is called as shunt resistor, and the resistance of this is written as RSH. R with the subscript SH. SH stands for shunt. Now, if you take this galvanometer and connect it across a resistor like this, which is called as a shunt resistor, this whole circuit is what is called as an ammeter. So this is what is an ammeter. Am I clear with that? Right? This is an ammeter. Now the question is, what should be the value of that shunt resistance that I need to connect? Right? That is what the important question is. So now we understood the basic. What is happening? We came from the basic saying that ammeter is a device which is used to measure current. And for measuring current, you are going to connect it in series. And the concept of ideal ammeter tells me that the value of the resistance of an ammeter is approximately 0. Right. So from there, we understood that the galvanometer's resistance should be decreased. But the question is, to what value it is supposed to be decreased? Right. When I put this question, what you're supposed to do is, you need to look at the ammeter's reading that you want. For example, if I look at this ammeter, so here it is written as A. A stands for ampere, right? Sometimes it will be written as MA, which is milliampere, which is called as a milliammeter. Sometimes it will be written as mu A, which is microammeter. So in this case, I have in amperes, and what are the least reading I have? 0, and the maximum reading I have is 5. Means this device can measure current anywhere between 0 to 5 ampere. So 5 is my outer limit. If I pass the current through the device greater than 5, it will not be able to measure. The reading will be greater than 5. So you cannot tell what is the exact value. Are you able to understand that point? So based on what is the maximum value of current that you want to measure for that particular ammeter, the shunt resistance will be chosen. For that, we need to derive a formula. Let us say the value of current that this ammeter is supposed to measure is I. Now, what will happen is this I will enter the junction, and at this junction, the current will get split into two parts. according to Kirchhoff's first law, right? And if I take this current to be Ig, where this Ig is called as the full scale deflection current. So what is it called as? It's called as full scale deflection current. Means you remember the galvanometer, the zero is here, no? Let's say 30 divisions are there. You need to pass the current through the galvanometer so that the pointer goes and stands at 30. So that's what is called as full scale deflection current. Okay. So this is Ig. So how much will be the current that is flowing through the remaining part? Out of I, Ig is gone here. I minus Ig will come here. Is the point clear? Now, if I take this to be AB and if I take this to be CD, the potential difference across the point AB and the potential difference across the point CD, aren't they going to be the same? Why? Because they both are connected in parallel. So can I write VAB is equal to VCD? Makes sense? So what is the value of VAB? IG into RG. So Ig into Rg is equal to, what is the value of VCD? VCD is going to be I minus Ig into RSH. So I minus Ig into R shunt. So what should be the value of R shunt? So it is going to be Ig into Rg, the whole divided by I minus Ig. Am I clear with this point? So this should be the value of the shunt resistance that you need to connect, for which it is logically known. They'll give you the value of the full scale deflection current resistance of the galvanometer. So what is the value that will keep changing? If you want to change the ammeter, right? If you want the ammeter to measure only between 0 to 2 ampere, what will you substitute? Here you need to substitute 2. Means to the same galvanometer, depending on the maximum limit, you keep changing the value here, right? You will get different values of shunt resistance that can be used here. Is the point clear? Right? So this is all about conversion of a galvanometer to ammeter. Okay? Make a note of it. Is the concept clear? So do you want to talk? So the next question is about conversion of a galvanometer to voltmeter. In a similar way, we will see what a voltmeter does. Voltmeter is used to measure. So voltmeter is used to measure potential difference or simply voltage, right? Next is, how is this device connected across? So it is connected in parallel, right? And what happens to the ideal voltmeter's resistance? Resistance of an ideal voltmeter is going to be, it is supposed to be infinite. So it is supposed to be infinite, right? Now, what happens here is, generally, when you talk about an ideal voltmeter, right, it is going to be infinite, but for a real-time voltmeter, it will be somewhere around 5,000 to 6,000. It will be that high, okay? Now, having said this, since our job is to convert a galvanometer to a voltmeter, so galvanometer has a resistance of somewhere around 100 to 110 ohm. Now you need to convert this to how much value? You need to take it to 5,000 or 6,000. Means you need to increase the effective resistance. So what are we supposed to do? Take a galvanometer of resistance Rg, and across this connect an other resistor which is Rs. Okay, it's called as a series resistor, and it should have a high value. Because if this is 100, you want 6,000 here, what should be the resistance of this part? See, if this is 100, this is 6,000. So you need 5,900. So it should be of high value. You need to take a series resistor of higher value and connect it in this way. Right? So that this whole circuit is what is called as a voltmeter. That's it. So this is what is called as a voltmeter. Now the next question is, this is the device which is going to be connected across any device in parallel. So whatever is the potential difference between the terminals of this voltmeter is going to be the required potential difference that you need to measure. Am I right? Now, the question is, whenever you take a galvanometer into consideration, the first point that you need to make a note of is, the current through it is always supposed to be only Ig. That is the full scale deflection current. So what should the current through the galvanometer be? It should be Ig, which is the full scale deflection current. So in this case also, the current through the galvanometer will be Ig only. Because the current through the galvanometer is Ig, current through the series resistor will also be Ig only, because in series the current is the same. Right? Now, this VAB is there. No? This VAB will tell you what is a maximum potential difference that particular galvanometer can, that particular voltmeter can measure. Now, if I take this device, again, I'm having a voltmeter here. The value is between 0 to 5. So the maximum potential difference it can measure and tell us is 5 volt. So depending on that value, right? So what is the maximum potential difference? VAB is equal to, in the example that I showed you, it is 5. Let me call that VAB to be V itself. So this V is what is 5. I hope you are able to understand. This is the maximum limit that this device can measure and tell us, right? So V will be equal to, it's a very simple expression. The potential difference between these 2 points is equal to, V is equal to IR. It is equal to the current through the galvanometer multiplied with the combination. That is going to be Rg plus Rs. So in the previous case, what did we do? We calculated what should be the value of the shunt resistance based on the range of the ammeter. In this case, what are we supposed to do? Measure the value of series resistor based on the range of the voltmeter. So RS is what you need to calculate. Bring IG to the left-hand side. This implies V divided by IG is equal to RG plus RS. And the next step is going to be RS is equal to V divided by IG minus RG. So V divided by IG minus RG. So in this case, what are we supposed to do? Take V is equal to 5 volt, substitute it here. IG and RG are known to you. So if you keep changing the value of the maximum capacity of the voltmeter, maximum reading it can give us, then the value of RS will also change. Okay. So this is all about conversion of galvanometer to voltmeter. Okay. So just make a note of it. Done? So next is we'll go to the, see, this is the last concept that we are going to see in this chapter, Ampere's circular law and its applications. Okay. So the next topic is going to be Ampere's circular law. Okay. Generally, whenever you take the concept of finding the field in a particular chapter, right? So in the chapter, you will always have two laws. See, for example, if I take the first chapter, you have Coulomb's law and you have Gauss law, right? When do we use Coulomb's law? When there are point charges. So the question is, can't we use Coulomb's law when we have extended charges? The answer is you can use it, but the only thing is there is a slight complication with respect to the mathematical operations. All that you need to do is take small element and then integrate and do that. So to solve that problem only, wherever there is symmetry, what came into picture? Gauss law came into picture so that you are able to get the same answer in lesser number of steps, right? Because Gauss law speaks about electric flux. In a similar way, in this chapter also, if you see, there is already a law which is there to calculate the field. What law is that? It is the Biot-Savart law, right? So if you observe this Biot-Savart law, it speaks about mu naught by 4 pi ideal sine theta divided by r square, right? It gives you a mathematical expression where you need different parameters, and you will be able to calculate the magnetic field due to a small current carrying element at different point. So if you need it for the whole conductor, you need to integrate. So it's slightly a tedious process, right? In order to simplify that, wherever there is symmetry, similar to what Gauss law speaks about, in this chapter, we have something called as Ampere's circuital law, or you call it simply as Ampere's law. So are you able to understand? So this Ampere's circuital law is almost similar to the way the Gauss law is defined, but there is a slight difference. Observe what it is going to be. So it states, this is put no, this integral, in the case of Gauss law, we call it as loop integral. Here we call it as line integral. So the line integral of B vector dot dl vector, right? What did we use in Gauss law? I'll write it in parallel so that you are able to relate it. E vector dot dA vector is equal to 1 divided by epsilon naught times charge enclosed. 1 divided by epsilon naught times charge enclosed. So instead of loop integral, you call this as line integral. Instead of electric field, you have magnetic field. Instead of area, you have a small element. So line integral of B vector dot dl vector is equal to, remember in physics, wherever 1 by epsilon naught is there, it is replaced with mu naught. So 1 by epsilon naught will come for electric field, mu naught will come for magnetic field. So that is mu naught times, here instead of charge, we will replace it with current. So we write it as I enclosed. Okay, the proof is not needed. So what does it state? The line integral of B vector dot dl vector is equal to mu naught times C current enclosed. So here, when I say charge enclosed, we say charge is enclosed by the Gaussian surface. In a similar way, here I enclosed is there. No, I enclosed is going to be the current enclosed by Amperian loop. Okay, so here you call it as Gaussian surface, here you call it as Amperian loop, right? So it is almost similar, right? Except the fact that the fields are completely different and the permeabilities and permittivities are different. So this is going to be the statement and the mathematical expression for Ampere's circuital law. Is the point clear? Right? Just make a note of it. Is that point clear? Shall I proceed? Right. So now we, right. Shall I proceed? Yeah. So listen. Now we'll see the application of it. Yeah. So now we'll see an application of Ampere's circuital law. Right? So if you observe, let's take a straight current carrying conductor of infinite length. Okay. And let's say the current through this is I. So if I take a point P here, which is at a distance A, right, from whom? From the current carrying conductor, then what is going to be the magnetic field due to the system at point P? So what is the magnetic field due to the system at point P? We already have a formula. It is given by mu naught I divided by 2 pi into A. Right? This we have already derived using the Biot-Savart law. Right? If you recollect it, the first one that we have seen is sine alpha plus sine beta. From sine alpha plus sine beta, by substituting the value of alpha and beta as 90 degree, you will get mu naught I by 2 pi A. It is a special case, right? But this is a very important formula because this is the one we'll use it in many problems. Okay. Now, what I'm going to do is, since this expression is derived using Biot-Savart law, our objective in this case is to apply the Ampere circuital law and get the same expression. Right? So for that, first step is, what you need to do is, after you consider the point and the distance, right? The first step that we need to do is consider an Amperian loop symmetric to the current distribution. So you need to consider an Amperian loop symmetric to the current distribution, and you need to ensure it passes through the point where field is expected. So it should pass through the point where the field is expected. So using the same logic, with respect to this current carrying conductor, what is the kind of Amperian loop I'm supposed to consider? The Amperian loop that you need to consider will be a circle like this. Is that point clear? Right. The second step is find direction of B vector using right hand thumb rule, right? Using the right hand thumb rule. And you need to consider an element dl on the Amperian loop, right? You need to consider an element dl on the Amperian loop and assign the direction to it, direction to dl, right, should be assigned in the direction of B vector. So you assign the direction of dl in the direction of B vector itself. So what am I supposed to do here? So I will consider a small element dl, and to this dl, I'm going to assign the direction. But before that, what am I supposed to do? If I apply the right hand thumb rule, it says that the magnetic field is going to be into the plane. So at this point, it is in this direction. So since it is in this direction, I'll draw a tangent at this point, right? I'll draw a tangent to the Amperian loop. So So tangent to the Amperian loop is drawn in which direction? In the direction of B vector itself. Is that point clear? Right? So third step is apply the line integral of B vector dot dl vector is equal to mu naught into I enclosed, and for I enclosed, what you're supposed to do is find the total current enclosed by the loop. So in this case, how many current carrying conductors is this conductor covering? It is covering only one current carrying conductor, right? So what is the total current that is covered by this Amperian loop? It is I, right? So I'm going to apply this formula. Observe. So tell me one thing, are these two steps clear? I'm doing it parallelly. Are those two steps clear? No. The third step is line integral of B vector dot dl vector is equal to mu naught times how much? Charge enclosed. So the line integral of B is B only. What is the angle between B and dl vector in this case? It is 0 because we consider dl vector tangential along the direction of B vector itself. So B into dl is equal to mu naught into what is the total current that is flowing through this? It is I, right? So you take the point P anywhere on this loop. Since the distance is going to be the same, magnetic field is a constant. So it can be taken out of the integral. So B into the line integral of dl is equal to mu naught into I. Did you understand this concept? Right. So when I take all these dls and keep adding it on this circle, what am I going to get? I'll get the circumference of this circle. So what is the circumference of it? So B into 2 pi a is equal to mu naught into I. B will be equal to mu naught I divided by. So it's the same result. Got it? So instead of using many steps, we can do it using this logic itself. Did you understand? So make a note of it. Finished? Okay. Done? Okay. See, there is one last topic that is left out, which is called as magnetic field due to a solenoid. Okay, so that will take at least 20 to 25 minutes for me to teach. But in order to save time, it is already recorded properly. Okay, so I'll give that video alone this week. I'll put it in the group also. Watch that video and come. So that from next class, Monday, Tuesday, Wednesday, I want to concentrate more on problems. I'll do all the problems for all the expressions that you have listed because there are too many formulas, it will confuse you. So what I want to do you to do is next 3 days concentrate on revising all the concepts. Monday when you're coming, come prepared for doing problems. And the following week, that is not this Saturday, the following Saturday, there will be a test in this chapter. Is the point clear? So whatever is needed for the test, I'll help you with all the problems. So come prepared. Any questions? Is that clear? So solenoid alone, I want you to go through the video and come. Okay. So is there any other question? That's it. So we'll wind up for now. Because you're integrating with respect to value. Just the put that so. Then Elma. Unit vector meaning null vector magnitude okay. Direct source null vector magnitude 1 and ES null vector has no magnitude, then how will it be? Yeah, we can wind up. Why are you there?